see what happens. I can also go to the YouTube. We are very advanced today. Doesn't say anything yet. Yes! Live now. Great. Okay. Okay. Yeah, if someone you try to go to the YouTube channel, you probably remove the sound. Yes. Okay. So it's working. Okay. So maybe I should just, while Aki is setting up, just welcome all of you. So. Yeah, it's good to also get some food.
Jeg tror, at mikrofonen er skruet ret meget ned. Det går det til test.
Ja.
Ja, det headset, jeg kan teste det.
Okay.
Yeah,
so welcome to 2018. I have to look in the calendar every day to remind me what year it is. 2018. Time's running. So this is, I think, welcome guys. Hi. Yeah, so for external students, I should remind you to actually check your DTU email when you are signed up. Because I sent out a message yesterday about the room.
We haven't gotten the login for the DTU mail yet.
Ah, okay. Well, then I'm extra happy to see you made it anyway. That's a sign that you're definitely qualified to be a PhD. Because that requires a lot of improvisation skills. Okay, so I think this is maybe the fourth time we run this course. Yes. And it's really great pleasure to have Aki here. Aki, as you can see, is a co-author of this very famous book. So it's really the first-hand teaching we get on this. The previous years we actually had 5 weeks of Aki here. But lucky for Aki, not so lucky for us. Aki don't have to travel so much anymore, so we'll do it in 4 weeks. But I think we have also tried to...
Speak up.
Okay, speak up. Okay, yes. We can also, yeah. We can... now you distract me, but... I think we have done it so many times now, so we kind of know kind of what is necessary. So I think we can actually do in 4 weeks. This is both like a curriculum based on the book, and also it's a project based course, right? So quite fun. You will go through some labs, some exercises, and then we'll do a project, and preferably it will be a project on some data from your PhD. Aki and I will kind of go through your project proposal and talk you about how to do the project, and sometimes we maybe encourage you to find some other data than your PhD data, because it might be that it takes too much pre-processing and so on to actually start working on your own PhD data. But we'll talk about that later on. But we have found out that actually we can do this with Aki here 4 weeks, and if needed, then we can actually have some of the exam, which will be like a project presentation from you. We can do that with Aki remotely on Skype. So that's the plan.
Yeah, I'll tell more about the practical details. And
so I think I'll stop speaking now and we can just get started. And I should also say one more thing is that actually just before you came, I got a mail from the administration that they have found a room for us. I'll send that message about that room out after today, or maybe during the teaching today. So we'll be in a nice room in 303 next time. But I'll send out a message about that. So, yes, please.
Okay, good afternoon, everyone. So we are here, or indeed, room later Mondays, Thursdays, and here are the weeks when I'm here. There were other constraints affecting that. These are now the 4 weeks, which means that this is slightly more condensed than previous years, but then you have also time for the projects after the last week. prerequisites for this course. You should already know the basic terms of probability theory, and there is also already for the Thursday you need to do one assignment where you need to answer some questions defining some of these terms and do some simple calculations using basic probability calculus. So you can check that you remember these, because I assume that everyone has taken some course with these things. And then if you find out that you don't remember, you still have time then to refresh your memory on these topics. I also assume that you know R or Python. The MATLAB is not allowed anymore. And also then this first assignment has some assignment for testing that. And so and then that you, so since these are all prerequisites, it's also so that you need to do it also already for Thursday. So the course contents that's based on Bayesian data analysis book, and these are the chapters we go through. And in addition, what is not in book, there is, you can learn the workflow Bayesian data analysis, and there is also some extra material. The book was published end of 2013, and it's already outdated. Mostly, I think it's outdated because of my own research, but also some other people have made great research on these things. And then but the problem is that there is no other book which would be also then up to date. So we still follow this, but then there's the extra material for new things. And in that way, it's also, I would say that we rely less on this kind of thing, not going specifically in the details, the book, and also there's more of, in a way that if you are able to do assignments and the project work without the book, then that's fine. You can use also other reference material, but this is kind of shows you the outline for the course what we are going through. I also mention later other book you can also use if you think that you find this kind of difficult in the beginning. And so there will be links to more recent articles, demos, video lectures, and they are on the course webpage then. You should read those chapters beforehand, and as I said that if you, in a way that you don't need to understand everything in those chapters, but then when you don't understand something, then you are able to ask here, and I also go in a way these the big picture here, extra material, answering questions, and also if you then when reading the chapter you might then find useful these extra material available also or alternative sources. So there are demos for R and Python in GitHub. So for each chapter there are these demos which are very helpful for also when you make your assignments. And so that there's a lot of these helps for how to load data, how to plot data, how to make basic computations, and then you need just to modify those for your assignments. So is there someone who has not yet used peer grade? Okay, so have you heard about peer grade? Okay, I thought that it would be already used everywhere in Denmark. So it's this web-based system where you find the assignment instructions and you will submit your report there anonymously, and then after the assignment deadline you will grade 4 other assignment these handouts, and so you are grading each other. It has these rubric questions, so that there's a step-by-step questions you answer when you are doing the grading, and we've already now used this 3 times before on this course, and so we've also been able to tune these questions, and students been happy that in a way that it's easy to do this grading. In order then to that, when you are graded, if you think that you were graded wrongly, you can then flag that grading. You can press a red flag button, and then me and Ole can check these cases which you flagged, and then decide whether you were graded correctly or not. So if you're happy how you were graded, that's fine, but then you also know that you can always flag if you are unhappy. The peer grading, it's nice in that way that now you see also other reports, different types of reports, so you learn also from reading others' reports, and you need to also think more, because then you need to also think how you justify your grading. If you say that there was some problem, you need to always then also justify this. So it will also make your learning more active. And these assignments are then so that you do with R or Python and write a report, and then at some point there's also Stan. And for the Stan, in some of these meetings I will also help then with installation if you have problems with that. And the already mentioned that this is just the pass-fail course, so you just need to get enough points in the peer grading, but otherwise you don't need to worry that so much. So here are the kind of the type of exercises there are. I will come back to these kind of the topics we're going through. But in a way that when you are doing these assignments, you learn these basic scientific data analysis cases, how to do them in Bayesian way. If there's 2 groups, randomized patients to treatment or control group, and then treatment group is given some treatment, and then how to know if the treatment is effective. Then we can have also continuous value treatments, different dosages, which dosage is sufficient without too many side effects, could be a question. We might assume then that we get different effects for different patients. So the treatment effect might be different for male, female, child, adult, light, heavy person, and so on. So pass-fail, but minimum of 50% from this peer grade assignments, and then you need to make a project presented. So in a peer grade, in order to encourage you to make these grading parts well, so you get 70% based on your own submission performance and 30% on your feedback performance. So that you will get in hand-in score, so it's average the scores from peers, and now after the flagging, teacher may overrule the score for some specific question, and the different exercises have different weight, and they are also listed there. And you can also, from the peer grade help page, look more details how these are computed. For the feedback, you will get extra points if you are constructive. How accurate you are in a way that if you agree with others grading the same assignment, you will get more points. And of course, this is going to be a classic decision theoretical problem that if you want to agree with others, you just need to make as careful job as possible, and then it's more likely that you will agree. And then overall, you get also points just making the feedback, and you will get also so when you grade, then you will also get feedback about your grading, and then that gives also points, and if you also give feedback of the feedback, you will get points. And in a way now since you just need to pass, you probably don't need so many points, but please still do these feedbacks well, because that way you learn more. 2-3 student groups, so you make a report and presentation, preferably with Stan. Previous years some groups have also made other Bayesian inference tasks, and there have been also some interesting projects on those. Stan is not so handy for all Bayesian inference tasks. That's why then some groups have used something else. Right after this session, start forming groups and thinking a project topic, and then you can already Thursday tell if you have some idea, and I can then give feedback. In 5 weeks, when there's the 4th week of these meetings, you will then present already a presentation where you present what you are going to do, but then you have still time to do the actual project work after that. So the final presentations are then later. And here's the schedule. So today there will be the practicalities, and then there's intro to Bayes, a little bit about the first chapters. So Thursday you have already the first assignment deadline, and I'll talk more about some basic Bayesian things. Then there's a 1 week, no lectures. Then we come to Monte Carlo, Markov chain Monte Carlo, and then for that you return already 2, 3, and 4. So you have there after this about 1.5 weeks to do 3 assignments, but they are from the kind of the easier ones. There will be then that week also more advanced MCMC methods and Stan, and then again deadline assignments, there's the model checking, predictive performance estimates, decision analysis, extra topics. And then the last week there's kind of the remaining topics, plus then you present your project plans. So there will be for each chapter there's a PDF which points out the most important parts of each chapter, which will reduce the amount of time you need for reading, additional links for extra material. Also, if you feel that you don't remember so well the basics of probability theory, you can also look. So Ben Goodrich is also one of the Stan developers, and he has video lectures, and these 4 first ones are already online, and then you could refresh your memory also looking at these videos for discrete and continuous probability distributions. Also, some students have said that they benefited a lot from reading Richard McElrath's book, Statistical Rethinking, especially the kind of the beginning chapters help them to start understanding also the Bayesian data analysis. So the Bayesian data analysis book starts with quite a speed, assuming that you remember overall something from the probability theory and like that. And then, so the McElrath's lectures, they are now all available for all these topics, 1 hour per each topic. So this might be also helpful. Okay, questions about the practicalities for the course?
You'll share the slides, right?
Yes, yeah. So right after or during the break, I can upload these.
The project you said is in a group of 2 to 3 persons, and the data set will be for one of the PhD students, or how is it going to?
Yeah, so it helps if it's related to your other research already, but you can also so that if for some reason in your group you can't agree that which data to use, you can use also something that doesn't belong to anyone's research.
Was it only the end project or also the assignments that should be done in groups?
So assignments alone, and only the project work in groups.
The assignments, will all of them be available now, basically?
Yes.
Or?
Yes.
So 1 to 8.
Yes. So they are. You can see all the assignments right now, and you can also submit them the answers any time you want.
Cool.
And when you do these assignments and write this handout you are going to submit, think that, would you like to read that handout yourself? So that's the kind of the level of clarity you should have in these handouts. But of course, it's not necessary that you would spend too much time on the how it looks like. It's of course more important that you just answer the questions but then that much clarity that you think that it's possible also easily to find answers to those parts which were in the assignment question. Okay, you can also ask more later of these practicalities. So my background is mostly my research is about the Bayesian theory, Bayesian methods, models and inference. My affiliation is probabilistic machine learning group in Aalto University, and these machine learning parts, my machine learning part is that I do also Gaussian processes, and even if they were used in the statistics much before machine learning term was even first time used, it's just that they've been used more in machine learning, and it's been easier to publish Gaussian process papers in machine learning journals and conferences than in statistics. So the Bayesian probability theory. Uncertainty is presented with probabilities. Probabilities are updated based on new information. Laplace said it's common sense reduced to calculation, although at that time it wasn't called yet Bayesian. The name comes from Thomas Bayes, who was English nonconformist, which meant that he didn't accept the state church, the ideas, and then because of that he couldn't get position in university, and so maths was hobby for him, but he seemed to be quite good based on the correspondence with other mathematicians. At that time there was interested in the problem that what's the probability that God exists based on if there are these miracles, so that if you see miracles you could then estimate probability that God exists. And this was the inspiration for this Presbyterian minister to study probability. Although that specific topic is not so much in this this posthumously published paper, they used the example of just a pool table, thinking about this inverse probability. He did not invent all, and Laplace invented this independently, but Laplace acknowledged this. This publication was first, and Laplace developed this much further. But then it can be also said that the modern Bayesian theory with axiomatic basis was then developed in 20th century. So earlier there was just probability theory, and the concept of probability was not strictly defined. It was close to this modern Bayesian interpretation, and kind of the interpretations of Bayes and Laplace were close in a way also this modern Bayesian interpretation. But then in the end of 19th century there was increasing demand for more strict mathematical definition of probability. So it was both a mathematical and philosophical problem. And then, in the beginning of 20th century, the frequentist view gained popularity. There are different definitions now what frequentist, specifically this one word, refers to. I think the good definition is that it accepts definition of probabilities only true frequencies and doesn't accept other definition of probabilities. And then these frequencies means that, like in a coin tossing, that you can throw a coin many times and probability of heads or tails is defined only based on that what's the frequency of heads in infinite number of draws. And then this definition gained popularity to the apparent objectivity, and because of the, it's also mathematically easier definition, this considering frequency in infinite number of repeated experiments. And so it gained popularity. It happened also that there were then specific data analysis problems where that assumption was fine. There were good books on that, and it gained popularity. And then in the 20th century there was then kind of strong arguments between frequentist view and then the other view, the older view, and then Ronald Fisher used then in 1950s first time term Bayesian to emphasize the difference to general term probability theory. He meant it as not a nice thing, but because alternative descriptions were longer, like talking about inverse probability and so on, it became popular and accepted that it's going to use. And then Bayesian started to use term frequentist, and then so there's the frequentist and Bayesian. Of course, there are also other views also, but we can say that these are the main views, and then there are also other views which are close to this frequentist. But so in the 20th century there was also then these rigorous mathematical proofs, axiomatic basis for the other probability than this frequency probability. I'll come back to this view soon. So the benefit of Bayesian approach is that, so in a way that there was also, because if accepting probability is only true frequencies, then it's difficult to accept priors. Yes, this inference we can use prior, but that's not even the most important part. This is equally important that integrating over uncertainties, and there will be examples on that, how in some cases, even if we don't have information, this integration part is also very important. That will make it easy to use hierarchical models, and then it's also easier to do model checking and evaluation in Bayesian framework. During the course, big part of the course is about the computation of expectations. So we need to compute this kind of expectation theta given y, and then the expectation of some function of theta. I will come also the notation in more detail later. And then in the book, it starts with these analytic forms of computing these expectation integrals, but then we have more about Monte Carlo, Markov chain Monte Carlo, and we don't have time to go to these distributional approximations, so I only in the end mention a little bit about them. And then we go through what is probabilistic programming. So it's a way how we can focus on describing the model through specific programming language, and then we can have an automatic inference, for example, like in Stan, or have a user-guided inference. So there are tools which make it easier to make these kind of semi-automatic. Okay, so that's what's kind of the overview. What's coming on the course also, and now then to this the Bayesian view of uncertainty. So we have two types of uncertainty: aleatoric and epistemic. And then we can represent uncertainty with probabilities, and then we can update uncertainty. Aleatoric uncertainty is due to randomness, and this is kind of what we can also then use this frequency interpretation. So if I take a coin, so this is heads, this is 10 crowns, and if I flip it, and if I flip it again, I would guess that most of you would say that it's 50-50 chance that I get head, and that it would be again, when I draw it next time, that it's always random 50-50 whether I get heads or tails there. And we are not able to obtain observations which could reduce this uncertainty. Next time when I draw, it's again just 50-50 that is heads. We have also then the epistemic uncertainty due to lack of knowledge. I can now choose which side I put up here in my hand. There's no randomness now. This coin has some state, some side is up. I know which side is up. I don't have any uncertainty about which side is up. But I would guess that most of you would say that there's still 50-50 chance that it's heads or tails. And now, in this case of this epistemic uncertainty, we can have a different uncertainty for different observers, and I can show this. You can get information which side is up. Your uncertainty changed, but not everyone's. So we are able to obtain observations which can reduce this uncertainty, and two observers may have different epistemic uncertainty. And this is now this epistemic uncertainty is now which the frequencies then did not accept, but which is a natural part of Bayesian inference. Well, then the Bayesian inference includes also this updating uncertainty. Usually, I forgot to take I have a small bag with chips, red and yellow chips, and I forgot to take that with me, but you can imagine I have red and yellow chips in the bag. If I tell you that there's 20 red ones and 20 yellow ones, and then I would pick one from there, I would guess that you would say that it's a 50-50 chance that I will get red or yellow chip. If I tell some other that how many reds or yellow there are, we can compute the probability of red just by what's the ratio of the red ones and total number of red. And we assign a letter theta for that probability. And we could then, I could then take a chip, put it back, shuffle, take a chip, and this would be then this aleatoric randomness. It doesn't change the, we don't learn more about that. And then we have this notation P for probability. The bar here is conditionally. So if we know this theta, so the ratio of red and yellow ones, then the probability that next observation, so the next chip is red. In this specific case, it's the same as then this theta value. But then if I don't tell you how many red and yellow chips there are, there's epistemic uncertainty. So you don't know beforehand how many red and yellow ones there are. And you could then make some guesses based on the size of the bag, for example, that it's unlikely that there would be one red and a million yellow ones. And so you would have some guesses probably already. But also, if I pick a chip out, if I put it in bag and shuffle and take the next one, if I all the time more often take red ones out, that would give you some information about the ratio. And now this is the what we want to then compute. What's the how likely different ratios of red and yellow ones are after we observe red, yellow, red, red, and so on. And this is now called then the inverse probability, because in a way we had first this was the description, that was the probability if we know this one, but then if we don't know, and then we turn it around. So we are getting the inverse. And now it turns out that the optimal way to compute this inverse probability is the Bayes rule, where we have a product of this term, and the underlying part is normalization term, so that we get that this is probability distribution which sums or integrates to 1. And then there are these papers showing that the optimality of this Bayes rule and how it can be derived from just that assuming that you are accepting that you can compare two events and say which one you prefer more. Or simpler version where you just there's two events and you can say that which one is more likely, and then you can go from there. Now it's important to that there's also some specific thing that here I said that this represents the aleatoric uncertainty. So it was what's the probability of y given theta. But there happens something, we still use the same notation, but it's not exactly anymore the same term there. Also for the notation, if we drop the normalization term, we use the proportional to symbol So we use a sloppy notation where this py given theta notation is used to for two different things. So in the previous slide, this was describing the model, and it's a function of y given some fixed theta, and it describes then the algebraic uncertainty. But at the moment, when we are interested in what is our uncertainty about theta, how likely different ratios are, if this is the function so that we get higher p probability values for those thetas which we think are more likely, but then it means also that here, so this one was quite clear that this is a function of theta, so our prior assumptions say that how likely we a priori assume different ratios, but then this is now also then function of theta and not anymore function of y. So now we fixed the y. So in the previous slide we got observations red, yellow, red, red. So we fixed this, and now we look at this same thing as a function of theta, and then we call it likelihood. So as a function of theta given fixed y, and in this case the y were the how many red and yellow ones we observed, it provides information about epistemic uncertainty. It's not a probability distribution in that sense that it's not normalized, and that's why we needed also the normalization term. So it's unnormalized probability distribution. And so the Bayes rule combines the likelihood with prior uncertainty, and then we get the updated posterior uncertainty. Okay, to think about these terms, pick a number between 1 to 5 in your head. Ready? And then raise as many fingers. And was this now a surprise for you that how many fingers you raised? So was it random, or did you know beforehand how many fingers you raised after you made the decision? If you look at the how many fingers your neighbor has, could you predict how many fingers they have raised? Was that random? How many fingers they raised?
Sort of, yeah.
And if we would repeat this again, what you would think that how easy it would be to predict? Would it be completely random if you would repeat this again, and you would need to again choose some number of fingers to raise?
For the individual person, or for?
For example, that if you would look at your neighbor and then you would pick some number in your head and you would raise those many fingers, do you think it's completely random how many fingers they would raise? Or do you think that you could guess?
I don't think it's completely random, because you're most likely not going to pick the same number again.
Mm-hmm.
And maybe still nobody would pick 1 and 5. So you still have two numbers, which would be a lot better than just uniform.
Yes. Yeah. Humans are really bad of making up completely random sequences. There's a you know the game rock, paper, scissors? So if computer knows 3 previous choices you have made, it will start winning on average on these because it's so difficult to be completely random. If you would be completely random, then you would on average tie. So you would be winning as many games, but even with knowing 3 previous choices you made, it can predict better than by chance. I was drawing a coin. If we build a robot with very fast vision which can observe the rotating coin accurately, is the draw random for the robot? So if it can see and it can model the dynamics?
It can probably update the entire way through until just before it lands. So it gets better and better, the prediction, I guess.
Mm-hmm. Yes. Also, there was Percy Diaconis and his group. They built also coin tossing machine, which always produces deterministic result. So it's also possible that they are not always random draws, but also that it depends on who's watching that, whether it's random. They can get additional information. So this one I included in the slides when there was also many physicists in the audience, and some of you also might have read something about quantum physics. So you can now, during the break, think about this and discuss with your neighbor there. And during the break, come up with an example with both aleatoric and epistemic uncertainty, and then tell it to someone, your neighbor, these examples, and then after the break I will ask a couple of your examples you come up with. And so now we'll have a 15-minute break.
So we start again 10 minutes past.
Yes.
3.
Physics high school exam in 2011.
So you're telling me that you are not taught that in Germany, you're not taught about quantum theory in our high school?
I would think that by definition,
Når du ikke er dataklar, vil jeg lige se.
Nej, overhovedet ikke. Jeg skal jo først til at ved at lave en søgestreng. Så skal jeg skrive protokoller. Altså jeg skal udtrække data snart, men de skal jo skrive protokoller. Ja, og der er afsat 4 måneder.
Not from my research.
Epistemic, der kommer jeg sådan til at tænke på 5A.
Så burde man kunne huske det.
Ja, det kommer fuldstændig.
Ja.
Så er der ikke
Fuldstændig tilfældigt.
Nå, okay, for det
I would just think from my weekend.
Ja, men sådan ikke helt tilfældigt. Sikkert trafikken, ja.
Når man står der og venter, så virker det sådan fuldstændig.
Many people or many women like to be there.
Yeah.
So there's a very high likelihood that one of the parents or at least they
I mean, also thought
Det er
that
det. For eksempel trials er simpelthen randomiseret.
and
Der er helt sikkert en del, som så gør, at der er en forskel. Der er helt sikkert også med bias.
Hvis du laver en perfekt trial,
Ja, så er der ingenting.
perfekt randomisering,
Så er der ingenting.
så kan du sige, det er et eksempel på
so it's something with bar,
om du så kommer i gruppe A eller
something
B
like
eller
that.
C, ikke?
they would not make up a very like pseudo form or something. No one would say that, even though it is possible. I think it's related to the frequency of vocals that words they hear. That mama and are very easy for them.
Should we put the slides? Can you send the slides? Today's slides, maybe I can put them
I didn't
online.
So wouldn't that be epistemic some randomness in the sound?
For eksempel så fik jeg at vide, at der var helt meget trafik der var 5
I think epistemic would be if you observe all the children and look at what they do in general, and aleatoric would then be the individual. You don't really know what it will be.
Der er jo også alle observationelle studier.
But I think it is very likely that most of the children will say, let's say that the ranking is quite high compared to pseudophone or something. So you have some prior knowledge about that.
Vel.
Jeg tænker meget mere konkret.
Der kan være nogle regler, der gør.
Jeg tænker,
I would say a basketball player plays a basket. So epistemic is throw rate. So
Jeg afhænger af fabrikken.
Men der kan man også sige, hvis du har købt en pose forvejen, og så ved, at der var kun 10% brød, som der åbenbart var nogen, der havde gjort. Fordi
Jeg tænker sådan en non-deterministic process.
det havde i hvert fald til.
Fordi der var nogen, der havde sagt, at de røde viner var sunde, så posen er mange udsolgt.
Ja.
Because if you only have epistemic,
Og den information fik du sent.
Ja.
if you have only aleatoric, then it's a
Og tilfældigt er, hvis man får bind for øjnene, og så går ind i den der hovedgarden med de der M&M's i forskellige farver. Og man ikke ved, hvad for nogen det er.
Yeah, it's always hard, I think, when you think of something. It's easy to say it's a stochastic process where it's highly deterministic, for example, like coin flip. You know exactly what force it was hit, where the surface of and every wind flow, then you could always model it. But because it's too hard for us
Du
to
kan
say,
reducere den usikkerhed ved at lave observationer.
Ja, altså for eksempel, hvis du siger, okay, vi ved ikke det her, så nu observerer vi 500 af dem. Og så, ja, okay.
Aleatorisk.
Det er, når jeg kan godt observere 500 af dem, men du kan bare ikke bruge til en stil.
For eksempel en bil.
Det var kaste med en terning, ikke? Hvis du har observeret 500 af dem, så...
Det var ikke noget med 500.
Nej. Og imod, du er en skæv terning.
Hvad mindre er præcis, hvis det er en færtegn, så gør det. Hvis det ikke er, så gør det.
Så randomiseret trials er så et godt eksempel på, at epistemic.
Kan man prøve at reducere det?
Ja, eller du siger, okay, vi undersøger først de her 500 personer. Dermed så antager vi jo sige noget om den store population.
Ja, altså man forsøger at sige, at det eneste usikkerhed, der er, det er aleatorisk, og derfor, så hvis der er en forskel, så er det
til at starte med, der ved vi det ikke. Altså, vi antager, at nogen af det
ja, præcis, ja. Er det jo så det der med sådan noget null-hypothesis, eller hvad? Det med sådan noget, så skal man gøre.
How are you? I started last year in March.
Og spørge, givet lige Stig ikke har nogle data, fordi jeg prøver, at jeg har mine data, det er ikke klart, at
Do you think it's something aleatoric?
Altså, det gør at finde en artikel med et eller andet. Altså, jeg ved ikke...
Nej, det er jo ligesom, at de taget gæsset, så bare smadrer deres data. Det er så sindssygt. Jo, det var faktisk en finde en interessant paper, og så tage data, og så analysere på det. Ellers så var der faktisk
Should I put it in like just in a lecture materials, one long folder? How many slides index, and then we have the observations.
That's
I can also put it like week 1, week 2, week 3, subfolders.
It's still that
Bedring i symptomer, altså hallucinationer og bangeforestillinger. Det må jo godt gøre. Der er jo 300 patienter, der er masser af variabler. Så kan man se, hvad er sandsynligheden for, at du starter med bedring i symptomer. Det vil de gerne.
Okay, fine. Okay.
But we had the question, can you do
I'll fix that. So I'll put it in one folder. Okay, there will not be so many. Okay.
Men Bayesiansk er meget federe, det er jo, du kan give fuldstændig en god sandsynlighed. Ja, præcis. Men altså, fordi Stig snakker om det, det kunne være fedt at lave sådan en artikel. Det kunne godt gøre, det kunne være fedt at bruge det. Sendte sig i vores PhD direkte, men det er jo noget, jeg skal bruge. Ja, men det er alligevel noget der med folk, der kommer ind i det der
So, like, even if you wouldn't have any information,
hvordan går det egentlig, og går det bedre, hvis du får behandling? Vi har jo nogle kontrolgrupper derfra,
be better than
og vi tager alle sammen for behandling.
the question is,
Ja, det er forskellige behandlinger, det kan man følge efterhånden.
Altså man kan se på, om de har fået 1 eller 2 og så videre.
Ja, præcis, og typer og sådan noget, ja, om det overhovedet gør nogen.
Altså det har jeg en idé om, det ikke altid gør.
Ja, det tror jeg heller ikke. Det gør en forskel. Og det er nok nærmere, hvor skidt har man til at starte med, efter et år. Vi har
der er også et naturligt forløb i det, altså en psykose, hvor altså også mange
regression
mennesker
to
var
mean,
over.
ja præcis, ja.
Altså, så det der med, at nu har vi brugt 4 antipsykotika, der er gået 5 uger, nu er den gået over, hvor jeg sådan lidt,
Det var nok lige vel.
tillykke. Ja.
Det er ligesom, hvis du bliver forkølet og får antibiotika.
Vitamin C.
Det var, okay, du var nok gået alligevel.
Ja. Der er nogle gange, så er man sådan lidt, okay, hvad tror du, der var sket, hvis ikke havde fået vitamin C? Hvad var der sket i Sten her gang?
Der var du sådan
Ja.
Prøv at høre, Stig. De data ligger der. Hvis de gerne vil læse, så kan vi jo bare holde det på afdelingen. Lave noget fornuftigt, så man kan bruge sådan noget.
Should I just upload all of it now, or should I upload all of it now?
Yeah, you can upload it.
Yeah, and then we can then maybe you revise some of them.
Yeah, so if I revise, you'll make updates, but in a way it's
Yeah, it was the same name, just new version. Yeah.
Jeg ved ikke rigtig, hvornår jeg kommer på.
Det mig gik der ret hurtigt, synes jeg.
Okay.
Så det kan man sige.
Jeg fik sådan en 2 til 3 uger.
Og det kan være, du rendte ind i studiestart.
Sikkert.
Det kan være det derfor.
Sikkert.
Ja, for det er alligevel et par uger siden, jeg skrev. Og det ser ud. Og sådan lige 4.000 nye. Kæft, denne kurse tager dig. Machine learning. Så 2 år, tror jeg. 1 og 2, det var kun en skærm, så sad jeg ude på foran det, så jeg ville godt at sætte det ind.
No. I think I'll make a folder called slides, exercises, and course information.
you could observe
Because there's quite a lot of files.
getting here, which
Is that okay? Or
but on the folder it's
sorry?
folder called PDF.
if there's more windows.
And everything in one. Okay.
Jeg vidste, det var den her kvadrat, det var
Yeah, I mean that's a question where do you make the break on what you know, but if you would have to get without other information, how long it will take me to get here, and you would not get further information except the previous time. Because I think when you relate it to the child example, then if you know all the words and the distribution of them, which which the child is hurt.
But then you can still, I mean, if it's a distribution,
Yeah.
in your case, I think the randomness would be your energy level.
Yeah, I mean, there's lots of factors. Could be raining, it could be freezing.
Har du set den ting, som
It could also be a car crashing in front of you.
Vi snakker
And
om
the cycle is being really slow.
råd for anvendelse af maskinen.
So there's
Vi snakkede om
quite a lot of number of factors.
at lave et skrivende
Maybe I'm
til
running
sommer,
an 8 and then the cycle
og til
is faster.
juleudgaven af udskrift. Så skriver noget stil af råd til anvendelse af dyr sygehusmedicin. Og så skriver hun, og så skrev jeg i dag, at der er også devices, IT-indikator.
The state of the world.
And then you need to eye condition and the likelihood of the chain cranking after the days I traveled already with it. Getting a flat tire, so there's the likelihood of seeing something in my way I run into.
Hvordan man undgår at bruge medicin med dyre ting i. Altså, både altså blodskål, og religiøse
But that's what we had before, right? Is this something? What is really random?
Random generator in your computer.
And that's not random. Yeah. So what is really perfect?
Yes, the only limit is really the stuff that I
Pudsigt,
can
men
still
det er også meget
learn.
på mening.
Jeg synes da også, man har et etisk ansvar der. Hvis du kan gøre det uden, så gør
It's
du
the
det.
effort that I'm willing to put into.
Jamen, hvis man er opmærksom på, at det er
Ja, ja.
et problem, så kender alternativerne.
Men jeg vil så sige, det er heller ikke alle de der alternativer, som så kan bruges.
Nej.
Der er også nogen, der kommer med sådan noget med, ja, men så kan du lave dem på grantræer.
Det gør du bare. Du får ikke meget tid til det.
Der var ikke nogen grantræer døde, og derfor så
Everything is
siger
complicated.
man, at det er på grantræer, så
Because one of the critical things that I'm thinking looking at content is putting up it. And that's also the point that is that you cannot know before.
Det der cannabis, det går der med råd. Jeg synes, vi skal have Jesse og Stig til at tage en dunder på sin video inde på regionens hjemmeside. Det skal ud. Det skal lige sådan bredes ud, så der er faktisk det kan mok.
så kan de bruge også som livsstilsperson. Det er den lægestuderende, der fik medicin til cannabis. Og her er ham der ikke.
Ramtet studie, ja.
Altså en crossover pleje.
Ja.
Og
For
det
en
er
måned,
så
mens man
og nu skal I bare sidde. I skal bare sidde det.
god forskning. God forskning.
Ja. 2 besøgspersoner, crossover. Så er den hjemme.
You find it somewhere in some weird blog.
Hvor han er på styrke, så skal lave 2 gamle.
Altså, det er syge, de har...
Ja, det er også.
Altså, de kan bare have sagt, at det er neurologer og psykologer, og hvad fanden der nu skal bruge. Det er bare sådan...
Alle.
To get another example.
Jeg kan ikke, det er ikke også selv. Nej, jeg har kun taget første halvdel skolen.
Derfor har du også... Du må behandle dig selv og...
Jamen, jeg kan ikke udskrive medicin på online.
Det kunne jeg da godt.
Men det kan jeg ikke.
You're going to Cologne.
Jamen, det er
I think that's the biggest
Jeg har min kæreste,
crime.
der kan. Så okay, i stedet for. Jeg kan udskrive med fint mig. Så er det ikke mig, der og kæft, min morfar, han døde i efteråret.
I'm not interested to this, but I think I've heard
Meget hurtigt forløb.
cancer.
Han havde jo, palliativ på og sådan noget. Han døde der.
Okay.
Det var lidt anede ikke meget. Vi kunne godt det hele. Helt og ingen styr. Det var så
So who wants to tell the example of aleatoric example?
So there's a bus, for example. Oh, sorry. Go. Okay, like with the bus, for example, it seems a bit like if you're waiting for it, it seems random, but it's probably due to traffic changes or whatever. So you get more information about the traffic, you might have a better idea of when the bus is arriving. So there's at least an epistemic component to that. Maybe randomness. If it has a flat tire, that's pretty random, I guess. So.
Yes.
Yeah, I tried to figure out like a simple example with the dice, which reminds us a bit similar to the coin toss, where you have some kind of rate of success, which is and you don't know when what's called what numbers lead to success when you throw the dice. And so there is some kind of underlying rule that can give you this epistemic uncertainty, because you don't know the rule that maybe all rows above, all numbers above 3 will lead to success. So, and then the aleatoric uncertainty in this is just that you have this uniform distribution where you sample your dice from 1 to 6. I don't know if that's...
Yeah, that's fine.
Yeah.
And I just
You just a biased dice.
came up with another example, because there are cases where the same example can be kind of false, like in the we could say also in the quantum uncertainty that it can be considered by either aleatoric or epistemic case, but there are also many other cases. One of them is that when with a computer you generate random number, it can be considered for human mostly quite aleatoric. But if you know the algorithm, because they are actually pseudo-random, it's deterministic algorithm which is used. If you know the seed number and the algorithm, then actually you don't have any uncertainty. So there's also the case that the same process does depending on what you observe. If you don't observe the random seed, it's aleatoric. If you observe the random seed and know the algorithm, it's epistemic, and actually your uncertainty is 0. Now, when you now talk about these different examples, what I call this the art of probabilistic modeling, is that now what you now described just with the words, that it can be sometimes quite difficult to describe it in mathematical form. We need to have a mathematical form. We had the prior p theta. We had the model part was the y given theta, and from that y given theta, then if we know the mathematical form, we can then compute what's the likelihood term, so that if we fix y and theta is the varying one. So this can be the difficult one. And of course then it's often quite simple models used. After we have been able to do the mathematical form, it's easy to use the Bayes rule. It's in quotations the easy because we still have the computational challenge. So we just write the Bayes rule, or we write these different expectations we want to compute. In theory, we have the answer already there, but then it can be really difficult to compute these expectations. There's also, in a way that it's also a little bit of art how you check your model. Is the data in conflict with our prior knowledge? How do you present the model and results to application experts? So these are partly art. Here's an example of complicated model I've been involved with. It's wet age-related macular degeneration. It's in the kind of the bottom of the eye, where cells start to degenerate, and usually then in this case then the vision goes down really quickly. So you know these, when you have big letters and then smaller letters and smaller, and in those tests, if you don't get any medication, you quite quickly you can see only the really big letters only. Then, however, this degeneration had, so there was, partly by coincidence, because of some cancer drug had such effect on cells that someone came up with the idea of testing that cancer drug also for this case, and it seemed to help. And then the treatment is now such that this drug is injected in the eye with the needle. So they put the needle here. Yeah, I see that you would not like that. And so that you need to go once per month. So every month you will need to get another injection. And that works really well, so that even for those who had already had some degeneration and the vision had gone worse, they improve and then they get that vision back what they had before. So the only annoying thing is that you need to go to the hospital every 1 month and get the needle in your eye. And so in this case the study was about, could it be possible to make these injections less often? Even that would be nice. And now the modeling part comes here, that it is possible to model the behavior of the drug, that when you inject it somewhere, you know that then there's a certain amount of drug there, and then eventually the drug concentration gets lower and lower. And then on the other hand, you can make these experiments that how many letters the patients see. And here the model is using ordinal differential equations, so that it can also, it is modeling how fast this drug goes away, and then based on that it's possible then to in a way predict that after injection what's the concentration at different times, and then on the other hand then first the concentration would go up and then it would go down, and then if you wait too long then the vision starts again to go down. It turned also that different patients seem to react to this drug differently, so that it's not just about the concentration, it's also that how well it helps different patients. And additionally, it's possible to combine results from different studies, which had that problem that other drug companies don't reveal complete data. They publish only article where there's only average results, and then you need to also kind of classic meta-analysis is based on assuming linearity and Gaussian, and then now the OD is nonlinear, and you need to be able to combine these two. These also so you see that there's quite many different things, and it's possible to have the like this even more complex differential equation models also part of the model. and of these all is that how we use all that information we know available to make these models. Sometimes it's also possible that instead of thinking so hard, we can use also flexible models. This is a gastrointestinal stromal tumor example. Various predictors available. Probability of recurrence in 5 years after surgery. And in this case, then model was much simpler, in a way simpler compared to the previous, where there were the differential equations and certain hierarchy and so on. So here, Gaussian process model was used, so doing this kind of machine learning type that just flexible, nonlinear model, and the data will decide then the shape of the predictor function, but we are not adding so much information as we could add in this pharmacokinetic case. I can show you the demo. So we have now there's a tumor size in centimeters, mitotic count, which is how many cell divisions there are per certain window size in microscope, and so that aggressive cancer has more cell divisions going on. Tumor site and whether the tumor was ruptured. Based on these data, there was from the patients, the Gaussian process model can be said that it's kind of just looking at the similar patients, and then based on the similar patients, we can, for a new patient, describe the risk. This is showing patients alive without recurrence. This is years after surgery. So if you have 10 centimeter tumor, mitotic count 20, gastric location, this shows then what's the probability that you would still be without recurrence after 1, 2, 3, 4, 5 years. I guess you can't see it in the back. And then, because we use Bayesian, we can have also the uncertainty about this, so that we can see if we go to, for example, when we have such values here that there are not many patients in the our observation set, then the uncertainty should grow. So we usually have more of those which did not have so bad case. This example that the less recurrence, or if we put then very big and also it's ruptured, we should have worse prediction, but also we see that there's not so many patients with situation like this, and then the uncertainty is also bigger. So sometimes we can add a lot of different information. Sometimes we use quite just flexible models which are more like about the similarity and so on. When we model something, it's good to remember that the model word itself refers to that it's not the same as the nature itself. It is some kind of simplification. If we drop a ball from different heights, and then we would measure time, how long it takes to drop, we could try to find some equation for what's the relation between the height and the time it took to hit the floor. We might then be able to come up with something that resembles something we could compute also from the like the Newtonian mechanics for rigid objects. But also we might be, it is possible that there would be also the air resistance. If it's like if you drop a balloon, it drops quite slowly. Shape and surface structure of the ball. Also, we know that the Newton's mechanics, it's not the true one. Relativity is the true one. But it's quite likely that in this room, when we would be dropping a ball, we can't see effect of relativity. There are man-made objects where this needs to be taken into account. GPS satellites need to take into account relativity in order GPS to work. If we have quite dense ball, and if we take the time using hand stopwatch, it's quite likely that we would be quite close to just this one and not even this. So you can see that even if we know that the true phenomenon is really complex, if our measurements are inaccurate, it's possible that we are not able to learn more complex things, or sometimes it's also that in a way the accuracy we need for our predictions is anyway good enough, even if we ignore more complex things. Here, it was beneficial to use this equation and combine with these other studies so that was able to make these design of experiments for the patients so that less patients were needed to find out that some of the patients can take the injection less often. Here, this was really more of the kind of the simple model. Even if it's a nonlinear and Gaussian process can sound complex in a way compared to these binary things, it's not that complex. Linear model is often good enough compared to using Gaussian processes or neural networks if the data is noisy and there's not much data. It's possible that we are not able to learn nonlinearity. So, taking into account the accuracy of the measurements, the amount of data, we need to think that how accurate model is needed. And there's the famous saying, all models are wrong, some of them are useful, so that even simple model can be useful to make useful predictions. Then when this probabilistic programming it's not even so recent, but it's now got more popular. There's the VAX program from the beginning of 1990s was also probabilistic programming language and the software, which was very influential, making the Bayes inference used in many applied fields. It made it so easy to make hierarchical models, and there were many applied fields where there was need for hierarchical models, and in those fields they were not aware of this philosophical disagreement between frequentist and Bayesian, so they didn't have any problems starting using Bayesian inference. They were just happy that it worked, and they didn't need to derive the inference. So they could just describe the model, and then the program made the inference automatically. So probabilistic programming language is a programming language designed to describe probabilistic models and then perform inference in those models. And so there has to be something that it's somehow easier to define probabilistic models, because otherwise you can define probabilistic models directly with any programming language, but then you would usually need to do much more. And so to be accepted that it's called, it has to have something which is specifically designed for that purpose. Usually they have also more efficient inference, and usually they have also support for overall workflow. So another example of there's another example of Bayesian inference, and then again using probabilistic programming software. This is apartment prices in Finland, and so that we can go closer to Helsinki region, and we can look at the apartment prices somewhere like here. There's quite many apartments sold. So there's the circle size here. It's the amount of how many apartments have been sold. It's a bigger circle. You can see that since there's quite many sold, the uncertainty in the price is quite narrow, and then it has some shape, and then it can make predictions in the future. So this is a region where people are interested in moving in, and the prices are going up. There's regions where there's not so many apartments, so no apartments sold at all during this period. You can see somewhere that, okay, here's where there's, you can see there's a small circles, and there's more uncertainty. This specific model is also then, you can see that it's not following exactly these dots, so it's making some smoothing, but it's also borrowing information from nearby regions. So it's assuming that there's a similar trend for regions which have similar zip codes. So this one and this one should have a similar curve, and they have. So you can see that this one has much less sold, but it has quite similar curve in nearby regions, and then these are where there's no sold at all are based on the nearby regions.
So does this model assume that the nearby regions have the similar price, or is it kind of the
And here's the region where they've just recently built apartment buildings. So that's why there's no salt. So it's just smoothing assumptions that nearby chip codes would have similar
prices.
What is it, similar parameters, so the similar increase.
Okay.
In the prices. And then they now have also then so this the what's the company who helps selling apartments? Is it term for that kind of companies? Yes.
Exactly.
So at least 2 of those in Finland are using similar kind of models to predict apartment prices, and in a way that they can then also give a better estimate for the customers that what is the reasonable price for their apartments.
Is it a linear model?
For this specific what they have in the internet, it's it has a linear and quadratic term, but they would like to have something better, but they haven't updated it. So this specific what I showed is just for demonstration. I don't know details of those real estate agency what they use. They don't tell.
You want to see data from before the crisis to see how the prediction is going before that. How it's changing.
Yeah, now there was also the time window was selected.
Exactly.
So that
Exactly. Yeah. And even just to see like because, when you can start seeing.
Yeah.
I don't think it's built for crashes. That
and of course you can include much more than just like now there was just a chip code. You could include much more about the services in the region and how quickly you can get from some region to city center and so on. So Stan is my favorite probabilistic programming language and software. So I will soon also show you example of that code, and then so you focus on describing the model and the data what you want to give to the model, and then computation is made automatically. So this for the Thursday we discuss more about these expectations and integrals. But the basic thing is that when I showed you predictions for the cancer recurrence or the apartment prices, there was some mean prediction and there was uncertainties. Also these uncertainty intervals, they are some expectation. And so for all these different predictions we also want to compute expectations, and we can compute these expectations so that we draw samples from the distribution of theta. So you remember we had this with the Bayes rule, we were able to get the distribution for theta, and now if we can draw samples from that distribution, we can compute expectations just taking empirical average, and we can also compute expectations of different functions of theta just by computing that function for each Monte Carlo draw. In the beginning we start with other inference, so the analytic integrals also, but then quite quickly we go to this Monte Carlo integration. So Stan is then using this Monte Carlo and very advanced Markov chain Monte Carlo methods, which will come during the course. There are different interfaces, and you will get familiar especially with MDR or Python. here's an example of code. Data block, we tell what kind of data goes in this case. We have a binomial model for treatment control comparison. So we tell how many there was in treatment group, how many of them died, how many are in control group, how many of them died. We have, and so this is kind of the same model as when picking up the chips from the bag. So I have a theta for the first group and theta for the second group. We can give also constraints. We can say that these thetas had to be between 0 and 1 because they were the probability of dying or probability of getting red chip. We can have priors, so there's more in the chapter 2 and 3 of these, and these beta priors for binomial model are in chapter 2. We tell that there's a binomial distribution for y. We can also compute additional generated quantities, and we will go to these details of different things here later. But in a way that this is, as you see, it looks like programming, and then based on this kind of Stan program, model program, Stan can make the inference automatically. There are also then, especially in R, there are different packages for making certain standard models with less code, and so the previous code can be also, when using RStan ARM package, can be written just like this. But it's using the underlying Stan model. It's just the some models can be made easier. Before I go to these questions at this point, so I will, in the end, spend little time reminding some about these probability theory terms, and so if someone feels that they know that really well, can also then leave. But before that, have questions, and then I'll also say something about the next Thursday.
In terms of speed, is there a difference between what kind of language you use to invoke Stan? Like, is Python faster than R, or is it all the same because it's called sort of behind the scenes?
Yeah, so the Stan, this underlying engine is written in C++, and this code is then transpiled to C++, so it's C++ speed everywhere. So no difference there.
It's also about the speed. I have seen some people, when they run Stan in R, they use multiprocessing or parallel processing, and I haven't been able to do that in Python. But also then I heard some lecture with Bob Carpenter saying that due to the fact that you use the Monte Carlo Markov chain, then you have to do it in serial because you can't really start the chain in more places than one. So just to ask, is it possible to run Stan in parallel, or should I just leave it? And
so usual recommendation is to run at least 4 different Markov chains from different initial values, and these can be run independently parallelly, and then and that's what happens in most of the interfaces. I can't now remember whether Python, so the PyStan supports also that, but if
not, it was already at least in development version.
All right, because it doesn't seem to do it by default.
Okay.
But,
Yeah. And so the so there are different levels of parallelization. So one thing is then that it's a good idea to run several chains from different initial values, and we will come to that later, that how it helps then to diagnose whether the sampling has worked, whether the Markov chains have mixed, and whether they are likely to have converged to the typical set. Stan is getting support for GPUs, so that's also, of course, in the GPU it's a parallelized computation. It's getting support for MPI, so even when you are running one Markov chain, it can multi-thread those computations. For example, if you compute, say, Poisson likelihood for 1,000 observations, then you can parallelize that when you have several cores, that kind of computations, because you need to anyway compute all the Poisson 1,000 Poisson likelihood values before you get the full log density and then go forward. Different, like the basic matrix operations will be then parallelized also, and so on. But then the limits in parallelization is that one Markov chain has to do sequential things also sequentially. So there are some limits that how much we can parallelize inference. And then there's also complications because of Stan computes automatically gradients for log density, and then that autodiff causes also some challenges then for parallelization. So that we need to also then in one log density estimate, the calculation also makes some computations in order, and then it makes parallelization always more complex.
So it's for the project, a potential project. Is that something like that, or what can you expect there? Like more, what kind of data?
And then now, when I said that, I hope that you start thinking about this project. If you feel too much confused about Stan, you don't need to start. So that you are, it's fine also that you will read more, and we have more meetings before you decide what to do. But because it's also now the that you might already have some certain problem you would like to solve. If it's your PhD thesis problem, it might be that it's in a way too challenging to solve your complete thesis problem here. But if you have some small parts from there, or even if you just know that there's something interesting in the data, you can just present that what kind of data you have, and then I can suggest that what kind of simpler analysis you could do using Stan. But then of course you will see also a lot of different examples during the course. So it's fine that even if you are later decide that what you want to do. And it's likely that there will, if you do it with Stan, it's likely that there's more lines, but it is also possible that some of you might be able to use rstan-arm or BRMS packages which support this kind of thing, so that it might be also that you can actually do quite few lines, and it's likely that you are not doing just one model, you are doing several different types of models, and then doing model checking and model comparison, that if some of the models have problems, and then I could show you one example. So this in a way that why it's possible that you make different models. In this case, it was a model for pest management system, and so there were roaches in apartments, and then there were 160 apartments with the treatment and 104 apartments as a control, and so that they used a set of traps to catch roaches, and then wanted to model how many roaches you will see after the treatment, and then in this case, what's the kind of the, so there were also other parameters. So there was the roaches before, there was the treatment, whether the treatment was given or not, and then whether the building was mainly for seniors or not. And this is now showing marginal posterior distribution, so that here's 0, and we can see, for example, here that this treatment and senior effect, the distribution is far away from 0, so we would say that it's effective. But here, this plot is showing that if we use the same model now to predict number of roaches in the future, and in this case we check that how often that model would predict that in the future we see 0 roaches. So it says that here in the probability of seeing 0 roaches based on the model is 0, while actually it was more than like 1/3 of the apartments had 0 roaches in the future. So in a way our model is not able to predict the data at all. And then there's the improved model shown in this notebook, and then that kind of same thing you might do, that even if the models are quite simple, you would intentionally start with the simple model and then do these different kind of model checking, and so that you are able to do those. And so these are, you can find a lot of these notebooks. I'll tell Thursday, I'll show you more about these R and Python notebooks, about these demos. And now it's We have less than 1 minute left, so I can take further questions, and then let's make it so that if someone feels they need some refresher for these probability theory terms, they can stay here, and I can spend like 10 minutes just telling specifically which are the kind of important things to focus on when you refresh your memory on these. And for the Thursday, so you should now read chapters 1, 2, and 3. But notice you don't need to read every section on those, so there are the reading instructions already uploaded, and you don't need to understand everything at the first reading. But when you, at least when you've gone through them, you will understand more what I have next time to say. So especially in this beginning, you will have a lot to read quickly because of this condensed schedule.
When do we get invitations to peer grade?
Today. So I guess Ulla has, so you can get the emails out of
CampusNet, yeah.
Yes.
Yeah, I can log into peer grade. I'm added also. You
I added you as a teacher. Yes.
Yeah, okay. I can try to. Sometimes it works when I write, when I press import from campus or inside. Yeah. Sometimes not.
Or we can I think the easier one is actually just we send the passcode.
Sorry?
So you can send from the CampusNet. You can send.
Which is now called Inside. Yeah. Yeah.
Let's do that. So I'll.
You mean that you can also extract an invite link from peer grade?
So it's possible to give out get a passcode so that we don't need to add emails in peer grade. We can just send passcode to everyone.
Okay, I'll look at it.
You said the deadline for the first assignment is this Thursday?
Yes.
Right? When are the deadline for the feedback, for the review, the peer review?
I think I put it in the next Sunday.
Yes.
Okay, so this many wants to hear a bit more. So I'll be a little bit quick. So I've noticed that often students confuse between these terms: probability, probability density, and probability mass. And now so the whiteboard. Can we get this? So I can go off a bit. Can you see the red one? Yep. So one important thing is to make a distinction between discrete and continuous distributions. So if you have a discrete distribution, so for example we would have now in the Okay, now we have a six-sided die instead of flipping coin. And then we would suspect that this is loaded coin, so that the probabilities are not 1/6 for each. But still, we have just 6 choices, and so we have probability for that we get from a coin a 1, or if this would be really loaded, we have probabilities like this. So now it's in a discrete distribution. This is always some probability. Overall, we have now probability distribution is describing then what is the probability for all these different values. For a continuous value, let's say this would be then the height of people. And then this would be, so this would be somewhere, let's say this is for men. I think for men it's something like 177 meters. And then different values here. For a specific value here, we don't have probability that someone is exactly 1.77 if we take into account also in a way that just exactly with zeros. Now it of course depends on our measurement accuracy. We could also measure so that if we round all heights to nearest centimeter, we would actually have a discrete distribution. But if we really model this as a continuous, then probability for this exact value is 0, and we have only density. And for a continuous distribution, we have probabilities only for intervals. And now we can then integrate over the density. So we can find out like theta between 1.77 and 1.8 probability for this. And now this is again the sloppy notation that we use. Same small p usually in different cases. And now we need to integrate over the density for p theta. So we can compute the probability that theta is between these values by integrating over the density. And now it's important to really remember the difference between density and mass. So density is in the continuous value, how high this is at some point. We can say now in the interval here there's some mass, but we can also now say that, so we can say that there's some probability that theta is here, but now we can talk about also probability mass for this interval. So same as for the humans, like 90% of my mass is below this line, but then in previous courses, many students have made a mistake that they might say that 90% of my density is below this line. And so you can think about this physical analogy between density and mass. For continuous things, we get mass only when we integrate over some interval. And so this comes because now we often use intervals to summarize distributions, so that instead of that we solve the whole continuous distribution, we might summarize it, for example, with 95% interval, And now it's important that you remember that it's 95% of the mass which is inside this interval, and on the other hand there's the so there's, for example, the highest density posterior interval where the density inside the interval is always higher than outside, but still this refers to amount of mass. Questions? Comments? And you can find even these definitions for these even in Wikipedia. Just kind of I wanted to say that it's important to make a difference between density and mass. For continuous distribution, we can say that we have a probability density function. For discrete distribution, we would say then that we have a probability mass function, because for each value, for each discrete value, we already have a probability. This will come also in Stan at some point for you, that you see that sometimes some of the Stan functions end in PDF and sometimes they end in PMF, and then you know that it's continuous if it ends in PDF and discrete if it ends in PMF. Often we don't want to specify separately whether it's discrete or continuous. Often we have distributions which are mix of continuous and discrete, and then we just talk about probability distribution. So then we don't, so these are more specific terms. Density function for continuous, mass function for discrete, and this is generic for both. Or we might specify discrete, continuous. Cumulative distribution function. Now, this holds both for discrete and continuous. So the cumulative distribution function is when in discrete case we sum. So cumulative for 1 is just the 1, cumulative for 1 and 2 is the sum of these, cumulative for 3 is sum of these. These are all the time in the cumulative. They are probabilities, but it's same for continuous. So if we start from minus infinity and look at the cumulative up to some interval, this is also now probability. So here, when we looked only at the one value, in discrete case, we have right away probability. If we look at the one value, we have only density, and we need to look always intervals. If we look at the cumulative, we get cumulative probabilities, and we get cumulative probability there too. I think the Bayesian data analysis book, really bad mistake was not to, when we went, so I was a co-author for the third edition, not on the earlier editions, and I tried to Andrew to add a bit more about these, but I should have been more persistent. So I mentioned the problem with the sloppy notation. Let's go here. So we in PDA most of the time we just write P, Y, bar, theta. Now there's a problem that Y can be variable or value. We could clarify using capital Y for variable and small y when we have a specific value also for that. Theta can be variable or value. We could clarify by using again the capital or small one, whether it's a variable or with the fixed value. P can be discrete or continuous function of y or theta. We could, in a mathematical notation, we could also denote that with function with respect to which variable it is, and also make then the difference between discrete, continuous. Now, this term is often called just the likelihood, but I wanted to, when I talked also about the epistemic and aleatoric inference, I wanted to make this distinction that when this has a fixed value, theta has a fixed value, and when this is a function of y, then this is not likelihood. And this could be then called sampling distribution or observation model. And this is the aleatoric part. Because this is now discrete, if we evaluate this function at specific value, we get the probability as I described there. If we now fix y and look at this as a function of theta, so now it's a function of theta, now we call it the likelihood function. It is also sloppy language that we often call, or many people call also this one likelihood. But it would be better to use different term, because then it would be more clear whether which thing is fixed. And now it's also important to remember that if this one was discrete, so if the observations we might see are discrete, it's still possible that the theta is continuous. For example, if we have this kind of idealized roulette, so that we would draw this kind of circle and make there the part of that, and then we would have an arrow we could spin. What's the probability that it stops somewhere there? And the observation could be inside some region or not, discrete, but then the probability, the theta, what's the angle there, is continuous. Then if we would have this more specific notation, so now small p, so that it would be continuous one as a function of y. Now it's a probability density function, sampling distribution, observation model with specific theta. If we evaluate it with specific y value, now it's a density. And if we fix y, but now we look at this as a function of theta, it's a likelihood function, and it can be discrete or continuous, depending on the parameter. And then why people use sloppy notation is that because y and theta both can be a mix of continuous and discrete values, it starts to look so complicated that then they decide to use simplest form and just write that it should be obvious from the context what we mean. But hopefully this will help now you that when you read that in a way that you know that it can mean different things, and for Thursday, if you find places where you don't know what is meant, then ask. And it's really important then that you just write these questions you come up. And this I already mentioned that likelihood is referred to also means something else than what is just a function of theta. Okay. So this was the reminder about these different probability terms, sloppy notation.
I just thought those were some really good slides there in the end, so I went to see the slideshow online, and it doesn't have the last two slides.
I changed the order of the slides.
Oh, okay.
So after Ole uploaded them,
yes,
I decided to change the order of the slides.
Yes.
But
So
I'll
it should be
upload
in
them
here.
in the new order.
Okay.
So the
Okay,
slides
it's
are
in here
there, but
somewhere.
it's just that
Okay,
the I thought that these are better to read in the end.
It's just it's nice to know.
Yeah. And now in your first assignment, the first question is just asking definitions of these.
See slide 32.
Okay. Okay, you put that in there.
But it still requires that at least probably some brain processing needed to get from these two. So. Yeah, I'm not going to say more unless you ask something. We are already 20 minutes past.
That was super useful.